Hello, and welcome to MAP 901's PSCR 2020 Tech Demo video. I'm Thomas Watson from the University of Memphis. Today I'll be demonstrating the prototype 3D scanner I developed over here, called Signac. It's named after Paul Signac, who co-developed the pointillism art style. This piece on screen is an example of his work. Signac is half handheld. The handheld platform features a screen on the back and two cameras on the front, which are connected to this laptop that records and processes the data. I've also got a keyboard, which lets me control the recording. The top camera is the Intel RealSense T265 tracking camera. Using its two sensors, it calculates the position and rotation of the platform, or its so-called pose. This technique is known as visual SLAM for simultaneous localization and mapping. Our brains have an exceptionally good SLAM algorithm as well, which lets both the camera and I figure out our position and our orientation in space by watching how the objects around us move. The bottom camera is the Intel RealSense D435 depth camera. Using its two infrared sensors, it calculates the distance between it and objects in the scene. Also, like our brains, it uses the disparity technique to do this computation. You can try it out yourself. Put your finger a few inches in front of your nose and alternately close each eye. You'll notice it moves left and right a little depending on which eye is looking at it. The farther away your finger, the less it moves. By measuring this movement, both the camera and I know how far away a particular object is. It also features a conventional color camera and a projector which projects random dots onto the scene to help the disparity algorithm. Signac's screen shows the user what the cameras are seeing and what they've scanned so far, which lets the user understand what remains to be scanned and identify any problems. And the laptop over here records the raw camera data and builds a low-resolution preview in real time to show on the screen. Once the scan is finished, the user can reprocess the recorded data into a much higher resolution version. Unfortunately, we don't have enough graphics power to display the high-resolution version in real time. So now that we've seen all the pieces of Signac, I'm going to stuff all the stuff in my backpack, and then we'll scan my office out here together. The bottom left image shows me scanning my office. The top left shows Signac's color camera, so you know what it's looking at. The bottom right shows the preview on Signac's screen, and the top right shows the final result, as if we had enough processing power to generate it in real time. I'm mostly looking through Signac's screen to understand what I still need to capture. I'm walking around slowly and carefully, as fast movements could upset the SLAM algorithm and make Signac lose track of where it is. Now that I'm finished, let's look at the final result. Overall, it's really impressive to me. I've missed some areas and there are some issues with the windows, lights, and shades. The color also looks a bit strange because the sensor isn't all that great. But for the scan speed and processing time, this is rather high resolution and high quality. Let's take a look at another scan. We'll look at one of the attics in Memphis' Pink Palace Museum, which is a large and very intricate 1,000 square foot space. In this next clip, we'll cut the attic's roof off and fly over it. On top is the result of a commercial LiDAR backpack style scanner, and on the bottom is Syniac's output. Syniac looks a lot better to me. Let's look though in more detail, this time with Syniac on the top and the backpack on bottom. Of course, Syniac's result isn't as simple to get. The complexity of the space upset the SLAM quite a lot and required significant manual correction. Syniac can see up into the rafters and down onto the floor because the user can point it wherever they want, but doing this takes a lot of time. Syniac does provide 30 times more points at a cost of 20 times less than the commercial scanner we used, though. To improve Syniac, we plan to get LiDAR-based depth sensors instead of the disparity sensor it has now. With more sensors and a longer range, the user won't have to move it around as much. We also want to improve the SLAM algorithms to improve registration and quality of the final result and reduce manual processing. We're going to shrink the computer a bit and remove some of the cables as well. So, we've seen how Syniac works, what it can do, and how it compares to another scanner. I hope you've enjoyed seeing it too, and thank you so much for watching our demo. See you next time!